I want to talk about some of work on the use of van der Waals layers for two types of spintronic devices that we're very interested in. And I'd like to acknowledge the students and postdocs in my group in the Max Planck. And I'd also like to thank Evgeny Zimbel and two of his postdocs who've contributed to part of the work I'm going to discuss. And look, if you look here, you can see this is where we make thin films, and in particular combine them with van der Waals layers. So I want to briefly introduce, originally I was going to tell you more about racetrack memory. Racetrack memory is a very interesting, I believe, technology where we want to build a device where we manipulate the information itself, which is stored in the form of a chiral spin texture. Most of the work has been done on chiral domain Waals, and over the last 20 years, we've evolved these structures which are made from thin, atomically thin heterostructures. And in particular, the most interesting racetrack memory is where you build a racetrack, which is a magnetic layer, from a combination of two layers, so that there's no net magnetization. And these are called, we call these anti-ferromagnetic racetracks. So here you can see this is a racetrack, let's say here, where you have regions magnetized up, regions magnetized down, and in between a domain wall, which we make chiral by the virtue of an interface Dzyaloshinski-Maria exchange interaction with a heavy spin orbit layer. And in the most interesting case is where we make one racetrack and a second racetrack, which is a mirror image of the first one, via an intermediate layer, which gives rise to a strong anti-ferromagnetic coupling. This is formed from a few angstroms of ruthenium. And when we pass current into these racetracks, we can move these domain walls synchronously at speeds exceeding 1 kilometer per second, making them a very interesting device to replace, in particular, magnetic disk drives. Then you can see this cartoon not working, where you would normally see the domain walls moving at high speed. So, in the last few years, we've mostly used optical means to detect the domain walls using Kerr microscopy, and so the racetracks are relatively wide, of the order of a micron wide. Recently, though, we've been able to incorporate anomalous Hall sensors into the racetrack, and we do this, I mentioned this platinum layer. These are platinum electrodes. This is the racetrack, which here is 73 nanometers wide, and you can see there's a platinum layer underneath, which is slightly wider than the racetrack, and depending upon that width, we can detect the domain walls through the anomalous Hall signal up to 20 times the distance from this point where we have the electrodes. So basically, we have a series of integrated sensing devices which detect the anomalous Hall signal from the magnetization, and as the domain wall passes by, the signal will go from one direction to the other. And what you can see in this top figure, what you can see there is an individual domain wall that we've moved along the racetrack, one by passing current pulses into the racetrack. So you can see this signal corresponds to one domain wall moving along the racetrack, where we move it in one direction by current pulses in one direction, then in the opposite direction. And as we increase the intensity of the current pulses, we need a smaller number to move the domain wall from one end of the racetrack to the other. And the point is that we can then position these domain walls individually to precise positions along the racetrack by tuning these current pulses. And our resolution today is of the order of 10 to 30 nanometers, and we can place one domain wall next to another one within 100 nanometers, which are dimensions needed for topological applications, for real technological applications. Now, in order to build a device, most likely we wouldn't use the anomalous Hall signal, which may be too small, although, as you can see, we can get giant signals from racetracks just 70 nanometers wide. Rather, we would incorporate into the racetrack a tunnel junction device, as shown in this cartoon. So here's the racetrack, a very short one. These are just electrodes to inject the domain walls, and the tunnel junction consists of a fixed magnetic electrode above a tunnel barrier on top of the racetrack, and as the domain wall moves through this region, then the tunneling current will evolve. And we can see, for example, integrate here a 100 nanometer wide racetrack, a domain tunnel junction, and the change in the tunneling conductance is about 100% as the domain wall moves from one side to the other side of the integrated tunnel junction as shown in this cartoon. This is the racetrack. It's about 100 nanometers long. And you can see that current pulses less than 500 picosecond long are sufficient to move the domain wall backwards and forwards very reliably. So we could, in principle, build a racetrack with one domain wall, and this could be as fast as the fastest memory today, which is static or random access memory. And so we've got basically a racetrack memory. We can build it at dimensions where we could store 100 domain walls per racetrack and build a super dense memory, or we could have a single domain wall per racetrack and build a super fast memory. So now I want to talk about this tunneling junction. So conventionally, we make tunneling junctions, and these would be the state-of-the-art materials today. They would be formed from electrodes of a BCC form of cobalt iron and a tunnel barrier formed from magnesium oxide. And when these are coherent, the electrons which tunnel through that MgO barrier are spin-filtered, because it turns out in body-centered cubic iron, the up and down spin electrons, one is mostly D-like, the other is mostly S-like, so the S-like electrons, which have more extended wave functions, can tunnel through the barrier. And recently, there have been some very interesting developments in the form, again, you need to build all anti-ferromagnetic tunnel junction to be technologically relevant. These types of junctions where you have magnetic moments, the stray fields from the magnetic moments cause interactions within and between tunnel junction devices. So these are not technologically useful unless you can eliminate the magnetization, e.g. with a synthetic antiferromagnet. Recently, we and others have worked on non-collinear antiferromagnets. These are typically Kagome systems where you have a Kagome plane where the manganese atoms in that plane form a triangular lattice, and because the manganese atoms want to be anti-ferromagnetically coupled, they form a triangular structure where the moments are oriented at 120 degrees to each other in a chiral fashion, and it turns out it was theoretically predicted that that kind of chiral system, even though it has no net magnetization, can do two things. One, it can show an anomalous Hall signal. We heard this very nice talks this morning about intrinsic time reversal symmetry breaking leading to anomalous Hall signals, and this is the same, roughly similar. Manganese-free tin itself is a vile semi-metal. On the other hand, you could potentially extract spin-polarized current from the surface of this chiral antiferromagnet, even though there's no net magnetization. This is through Berry phase effects. And there were two papers in Nature last year, one involving manganese-3 platinum, which is an FCC form in which, in the 111 planes, the manganese atoms form this triangular structure, and another paper was on manganese-3 tin. And in this, it's not clear whether this result will be confirmed, but in particular, manganese-3 platinum, this chiral antiferromagnet, was supposed to show 100% tunneling magnetoresistance. Interesting. We actually haven't been able to reproduce these results, but very interesting. So quickly, briefly, 2D. Let's move to 2D materials. And of course, the history of 2D materials is super interesting. A lot of interest in could you form a long-range state in systems? And the Mermin-Wagner theorem said no, but if you have anisotropy, then it's possible. In 2017, then the first 2D van der Waals magnetic systems were found. This is chromium germanium telluride and chromium I3, chromium chlorine 3. I want to briefly discuss these. These are super interesting systems because in a 2D system, you can make a single monolayer, let's say, in our case, of chromium chlorine 3, and this monolayer is magnetized in plane, and we demonstrated in this paper 3 years ago that a single monolayer we could take from our laboratory in a vacuum taxi to the synchrotron in Berlin, and we could measure using X-ray magnetic circular dichroism the critical exponent and demonstrate that this critical exponent was the first example of a 2D easy axis XY axis magnet. So very interesting, only made possible because this single monolayer of chromium chlorine 3, which we prepared by molecular beam epitaxy on graphene, is actually doesn't is not bonded to graphene. There's no bonding at all. In fact, the chromium chlorine 3 layer grows randomly oriented with respect to the graphene underlayer. So it's a very nice example of a 2D system. Another very nice example is this work by Shandong Zhu and Pablo Herrero, where they looked at this material, chromium iodine 3, which is a 2D ferromagnetic system in which a single monolayer is ferromagnetic, magnetized outer plane, and then two layers are coupled anti-ferromagnetically. You see, in this case, this hysteresis loop they showed, no net magnetization in zero field. Three layers, again, it's a net ferromagnet or ferrimagnet. And in particular, what they showed was that if you placed 1, 2, 3 monolayers between graphene electrodes, you could measure the tunneling current. And they demonstrated when you applied a big enough magnetic field, the tunneling current would change as you switched the magnetic moments from being anti-parallel, these are anti-ferromagnetically coupled, to being parallel. However, you can see in zero field, there's only one state. So this type of system, while theoretically experimentally very, very interesting, is not technologically very useful. So we wanted to solve this problem, and I also wanted to point out that this is a very interesting system in which you see the largest tunneling magnetoresistance effects at relatively high bias. Zero bias, no signal. You have to go to 300 millivolts to see a signal. Again, not technologically relevant. So let's just summarize. If we take a conventional ferromagnet, we have two magnetic electrodes separated by a tunnel barrier. You can see changes in tunneling conductance of up to 1,000%, at low temperatures a few 100% at room temperature. And these, with synthetic anti-ferromagnetic electrodes, form the basis for tunneling magnetic random access memory. So what we want to do is use this concept that Xiaodong and Pablo introduced, non-magnetic electrodes with a 2D magnetic barrier. And we're going to look at the tunneling conductance through that 2D barrier. Can we make a device which has two states in zero magnetic field? This would be technologically very interesting. So we want to look at a system in which we make a tunnel junction from two bilayers. Each bilayer is anti-ferromagnetically coupled, and we want to switch the magnetization of one bilayer shown here so that the two bilayers have their moments either anti-parallel or parallel. So we're going to switch one bilayer with respect to the other one. And how can we do this to create two states in zero field? We've demonstrated we can do this by twisting. So we've heard a lot about twisting. So this is a different use of twisting. And the way we do this, you can see here, this is the one bilayer. The second bilayer is twisted at an angle. So from the side, it looks shorter. And we can demonstrate that this system, if we choose the right 2D antiferromagnet, can form two stable states. And that's what I'd like to discuss in zero magnetic field. And the system we're using here is chromium sulfur bromine. This is a very nice in-plane anti-ferromagnet, but each individual layer is ferromagnetic. And you can see the layers consist of this. This is the structure shown here. The red atoms are bromine, 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 and the interior layers consist of the chromium and sulfur to form a single monolayer, which is ferromagnetically aligned in plane, and the next one is anti-ferromagnetic. That's the idea. So first, let's look at the case without any twisting. We simply take a bilayer, as shown here, and here is the bilayer, untwisted. We make graphene electrodes, top and bottom, and we protect the chromium sulfur bromine with hexagonal boron nitride underneath and here, and we make gold electrodes to the graphene electrodes to the bilayer tunnel barrier. And what do you see? Well, you see, just like the chromium chlorine 3 case, you see that the current is zero, very, very small, in the quiescent state where the bilayer, the two layers in the bilayer are antiparallel. But when you apply a big enough field, then you see a giant increase in the conductance when the two layers are parallel to one another. This system, however, is distinct from the chromium chlorine 3 and the chromium iodine 3 case. It has an orthorhombic structure, which means that in the plane of the chromium sulfur bromine, there is an easy axis. And this easy axis means that we could flip the magnetization by in this way. So first, if we just have an untwisted structure, temperature. We can measure for field going from one direction to the opposite direction. We measure the current through the device as a function of the angle of the field with respect to within the plane of this flake. And you can see here that the state in zero field is the same, whether we go from one field direction to the other. So there's no two states. The states are identical. However, if we twist the two layers at some angle, here we've twisted one bilayer on top of the second bilayer at 35 degrees, now you can see we can form two states where they're quasi-antiparallel or quasi-parallel. And if you look here, you can see as we switch the field, if we sweep the field over a wide range, then again, we don't see any distinction at zero field between the two states. They're basically the same. However, if we limit the field range, so the field is limited, so that the bilayer, which is essentially has a hard axis, that moment does not switch. And if we limit the field, we can only switch the moment of the bilayer whose magnetization is oriented along the easy axis. And in this case, you can see this is a plot then of the current. This black one is little current, red is a bigger current flowing through this vertical tunnel junction. You can clearly see here that this color here at zero field is very different for field sweeping in one direction than the other direction. So we've switched the magnetization of one bilayer, keeping the other magnetization fixed, and we can see changes in tunneling conductance then here of more than 200% here and up to approximately 700% if we make the twist angle smaller. So there's a compromise. The bigger the twist angle, the larger the field we can apply without switching one of the bilayers. But the smaller the twist angle, the greater is the tunneling magnetoresistance. And so this is shown here. This is the tunneling current as a function of the magnetic field in plane. And you see 10 loops, it all looks the same. So in zero magnetic field, we have a giant tunneling conductance, two states with a different tunneling conductance. So this is super interesting here, up to 700% tunneling magnetoresistance. If we have a small twist angle, this is an 80-degree twist angle, then the tunneling magnetoresistance is smaller because the two states are more similar to one another. That's the concept. So we've demonstrated very interestingly a tunnel junction from van der Waals materials, all anti-ferromagnetic, no net magnetization, which is therefore technologically very useful with a giant tunneling magnetoresistance. So let me just show you one other interesting experimental point is that if we compare the temperature dependence of the tunneling magnetoresistance, the black curve is the untwisted case. And you can see whilst at low temperatures it shows a higher tunneling magnetoresistance, it falls off very quickly with increasing temperature, whereas the twisted case, you can see there's a very weak dependence of the tunneling magnetoresistance. And that is because when we twist, it turns out the gap between those two layers significantly increases by 50%, and the bonding between the bromine atoms on either side is no longer, the bromine atoms no longer line up, and the conductance through the gap between the two layers becomes much smaller. So effectively, it's a much better tunneling junction. And this is why the tunneling magnetoresistance remains to very high temperatures, almost to the nail temperature of this device, which is 130 Kelvin. Whereas the untwisted case, you can see the tunneling magnetoresistance drops very rapidly. How do we account for this? And so we have collaborated or asked with Evgeny Zimbel at the University of Nebraska, and we came up with a method to calculate the tunneling magnetoresistance, and this basically involves the evanescent waves which propagate through one of these insulating layers. So this chromium sulfur bromine has a tunnel, has a gap of about 1 volt. It's a semiconductor, but it's also a very good insulator at low temperatures. That forms the gap. And the idea is that the wave function then will basically propagate through this insulating layer and will, of course, they will be diminished. And there are two possible scenarios. We have the case when the two magnetic layers, let's say we took a bilayer, the two layers now have their moments parallel, and then the wave functions, the electrons with spin up and spin down, will propagate differently across that barrier, whereas in the anti-parallel state, the propagation of upspin and downspin electrons will be similar. As you can see, one side of the electron can propagate more easily, but the second barrier, coupled anti-parallel, will prevent the tunneling of those electrons. This is the idea. So what do? We take chromium, sulfur, bromine, and we artificially put all the moments in all the layers in bulk in the ferromagnetic configuration, and we calculate the spin-dependent band structure. This is what Evgeny and his group has calculated. Of course, in the anti-ferromagnetic configuration, which is the energetically stable configuration, the band structure is unspin polarized. And so based on this, we can then calculate the propagation of the electronic wave functions through an individual ferromagnetic layer for spin up and spin down electrons in the two cases where the moments are parallel or anti-parallel. And we do this, we look at the evanescence of these wave functions, the decay function. This is what we're plotting here as a function of kx and ky. These are the two momentum directions in the plane of an individual layer, and we can calculate it through this individual layer for spin up and spin down electrons, as you can see. And so in this way, we can calculate the total transmission through this chromium, sulfur, bromine for the untwisted case. And in the untwisted case, we get about 1,000% tunneling magnetoresistance, which matches our experimental results pretty well. Well, then what do? We use these kx, ky momentum-dependent evanescent wave function dependence, integrate over the first layer, and then we twist the second layer, and then we just change the, reformulate the momentum for the second layer, assuming coherent tunneling, and then we can calculate the tunneling magnetoresistance as a function of the twist angle. And we find excellent agreement between this theory and our experiment. So this is the normalized tunneling magnetoresistance to zero twist angle as a function of increasing twist angle. And you can see this is the red dots are the experiment. So these are individual devices we've made with different twist angles. And the theory, the black dots from Evgeny and his group, you can see matches extremely well at low temperature. So this we think is very interesting. Now, that's one topic. Now, I think I have a few more minutes, so I want to now switch to a totally different topic, but relevant to racetrack. We want to build a cryogenic racetrack which operates at millikelvin temperature, and we want to use new physics from proximity-induced superconductivity of two types. First, I'm not going to say much about, but again, 3 years ago, we demonstrated that going back to this chiral antiferromagnet, where the manganese atoms have huge magnetic moments, we could build a Josephson junction. These are the blue niobium electrodes. This green layer is this chiral antiferromagnet. And we demonstrated that supercurrent, we could proximatize this chiral antiferromagnet into a superconducting state and see supercurrents flow over distances of up to 1 micron today, which is huge. And this is the field of spintronics and superconductivity. It turns out if you have non-collinear spin textures, it was theoretically proposed 20 years ago by Sebastian Bejeray in particular, that you could propagate supercurrents over long distances. And again, without going into any detail, it turns out that the superconducting proximity-induced state has a triplet component that allows these triplet supercurrents to propagate over these massive distances. I'll come back to that in a moment if there's time. I wanted to briefly discuss then this very interesting concept of a Josephson diode. So it was first shown in 2020 in the Kyoto group of Tero Ono that he made a tricolor superlattice, niobium, vanadium, and tantalum, and demonstrated a superconducting diode effect where the supercurrent flowing in one direction and the other direction was distinct. And we found that a variety of van der Waals systems, in particular nickel ditelluride and platinum ditelluride, which are Dirac semimetals, but more importantly, these have topological spin-polarized surface states. This is super important because to see a Josephson diode effect or a superconducting diode effect, you have to break both center inversion symmetry and time reversal symmetry. This material, nickel ditelluride, has neither broken time reversal symmetry nor inversion symmetry. It's a 1T, it's a trigonal system. So what do? We simply take a flake, shown here, of this, in this case, nickel ditelluride. We make niobium electrodes, a conventional superconductor, and we place these niobium electrodes on the same flake. Here you can see distances ranging from 120 to 580 nanometers. If we now measure the voltage between two electrodes, then when the niobium becomes superconducting, the voltage drops, and then the junction itself, the nickel ditelluride, becomes superconducting by proximity, and this temperature depends on the spacing of the niobium electrodes. The greater the spacing, the greater the distance the supercurrent has to flow, then the lower the temperature is needed to fully proximatize the nickel ditelluride between these niobium electrodes. Now, if we measure the supercurrent as a function, voltage as a function of the current flowing through the nickel ditelluride, you can see above some critical current, again, depending on the spacing, the smaller the spacing, the bigger the critical current. The critical current for the current flowing in the positive and the negative directions is essentially the same. However, in the presence of a small magnetic field, 20 millitesla, which has to be applied not parallel but perpendicular to the supercurrent, you can see here that the critical supercurrent density for current flowing to the right is 40% smaller than that flowing to the left. So it's a giant effect, and this is at 20 millikelvin. But if we have a smaller spacing, then the effect can be up to 80%. And this indeed means that if you place the current in between these values, let's say here, then in one direction it's normal, in the other direction it's superconducting, and in fact, as you can see here. So this is very nice. And since I'm running out of time, I'll just mention that in collaboration with Liang Fu and Yang Zhang and Margarita Davidova, we developed a theory which is based on second-order Cooper pair tunneling. And when that happens, you get a non-sinusoidal current superconducting phase difference relationship, which leads to this effect, that you get a diode effect. And it depends on these topological spin polarized surface states that the magnetic field basically leads to a broken time reversal symmetry, we believe. This is the idea. And this theoretical model predicts in particular how the difference in the diode effect, the difference in the critical current goes proportionately to temperature minus the proximity temperature of the nickel ditelluride to the part 2, and you can see our results fit this very well. Moreover, we can predict how the critical current difference for plus and minus currents, zero in zero applied field, increases with the field perpendicular to the current flow, then to a maximum value, decreases, crosses zero, and we have this fantastic oscillatory dependence of the diode effect as a function of these magnetic fields. And the magnetic field basically introduces a Zeeman splitting to the band structure through these topological surface states, we believe. And so back to the conclusion is that we could build a fantastically interesting racetrack memory operating at low temperatures to support quantum computing applications by using this diode effect as a sensing device for the magnetization in the racetrack, the domain Waals, and by generating spin triplet supercurrents through non-collinear magnetic systems such as this chiral antiferromagnet, we can generate triplet supercurrents that in principle can carry angular momentum and could be used to manipulate the magnetic domain Waals. This has not yet been demonstrated by ourselves or others. And so just a final comment would be, of course, Van der Waals are fantastic. However, we don't need Van der Waals. We can also see a giant Josephson diode effect in pure platinum. So we proximatize a thin layer of platinum by proximity to niobium in this case, and on the backside we make it magnetic by proximatizing it with an insulating ferromagnet, which is YIG. And in this case we see a giant diode effect, and I'm going to skip that result, very interesting, and then finally mention, to prove that this is an intrinsic effect. There's been a huge debate in the literature over the last couple of years whether it could be extrinsic related to flux trapped in the junction. We've made vertical Josephson diodes using exfoliated niobium diselenide. In between, we use the famous tungsten ditelluride. Again, this material is orthorhombic, very interesting, and therefore we have this mirror plane, and now we apply a magnetic field in the plane of the tungsten ditelluride, always perpendicular to the supercurrent that flows in this vertical direction, and what we find is we only see this diode effect when the field is along a particular orientation perpendicular to this mirror plane. And so it proves that the effect is intrinsic. Since I'm running out of time, I won't show you those data, but we have multiple data that show, again, that the diode effect only appears when the magnetic field is along this A-axis. We, of course, determine the A-axis after the fact by polarized Raman scattering. Okay, I'm going to skip that and just summarize, since we're running out of time. Racetrack memory, super interesting technology, and we're close to making it technologically relevant. We actually are supported by Samsung to do that. We believe it will be a technology in the next few years. And at the same time, Van der Waals is super interesting, in particular for making all anti-ferromagnetic tunneling junction with two non-volatile states. Giant tunneling magnetoresistance, which I didn't mention in this case, appears at 0 voltage, therefore technologically very relevant, has a weak temperature dependence for the twisted case. And then I also mentioned the Josephson diode effect, which is a very interesting phenomenon. Giant effects up to 80%, which could again be used at cryogenic temperatures as a detector, a novel detector. And well, there we are. Thank you very much for your attention.
Chromium sulfur bromide typically tends to be heavily doped.
No, it's not doped. It's undoped.
I see. But it's not a priori obvious to me that it would be better to have an undoped semiconductor versus a doped one. Do you know what the answer is theoretically?
Well, theoretically, for our tunneling junctions, we want it to be undoped because we want them to act as a tunnel barrier. If it were doped, then we would not see that. Of course, many Van der Waals systems, I'm not sure which doping you're referring to, but let's say the 2D magnetic systems, you can dope them with iron. Super interesting. It goes into the Van der Waals gap, and we've demonstrated we can see spin class behavior. Maybe it doesn't answer your question, but I think doping is interesting, not for semiconductors, but actually magnetic doping to generate novel magnetic states.
So Stuart, since the conventional MTJ is already, that you made, is already reaching such a high value and has been used already in MRAM, so what do you exactly think we can gain by doing this anti-ferromagnetic Van der Waals MTJ? Are you gaining the speed or the low stray field or what?
So that's an interesting question. I think these all anti-ferromagnetic are very interesting because they're single layers of these very complex materials. Impossible, nearly impossible to make by, let's say, molecular beam epitaxy for this reason, always doped. And they're not interesting when they're doped. You have to make them undoped. So it's super interesting to imagine systems like this where you have no net magnetization, yet you can extract highly spin polarized currents. Maybe this isn't the one that could be used technologically, but it has super interesting properties, all the properties you need. And it's simpler than the conventional. So I showed you a conventional tunnel junction, copper-ion, MgO copper-ion. In fact, there's 10 other layers to make it useful. You have to make each layer from a synthetic antiferromagnet, non-trivial. Here you have a system where you automatically have an antiferromagnet. So these types of new Van der Waals antiferromagnets, or even more interesting are the chiral antiferromagnets, where you can extract, in principle, if you can extract spin polarized current, would be super interesting technologically. They would be the most technologically relevant materials, the chiral antiferromagnets. Single layer would be simpler to make, in principle.